Artificial intelligence has become the buzzword of the day and the topic that stands to change all of our lives. Whereas much of the conversation with AI is around applications that reside in server farms, there's an enormous opportunity for Edge AI to bring new capabilities to our embedded designs as well. It seems these days you can't turn on your TV or look at your social media feed or really do anything without being inundated with AI. It seems like all society really can talk about right now. And what's that going to mean for us and our future and the entire world? And I think there is no doubt it's going to have a huge impact on our lives, and in some ways already is. But a lot of the conversation going on right now that I see anyway seems to be more geared towards the AI that still resides in servers, the large language models and generative AI and all of those kinds of things that make cute little pictures on your Facebook feed or whatever your aunt is doing somewhere on the planet. But what I think is going to be much more relevant to us as embedded engineers is what's happening in Edge AI. And that's where AI really, I think, is moving from just what's on our cell phone screen or laptop screen, and AI moving into the physical world and into our embedded systems, which I think is going to be really exciting and something that we need to take the time to learn about, think about, and determine how we're going to implement that into the next generation of our products. Today, I have the great privilege of speaking to a good friend of mine, Steve Totosian, Senior Vice President of IoT and Compute and Wireless at Infineon, a fellow Austinite and somebody that I've had the privilege of working with for a long time. So, Steve, great to see you and appreciate you joining me on The Current today.
Thank you, Todd. Really pleased to be here.
So let's start with, again, I don't want to do another buzzword. I'm not a huge fan of buzzwords. The buzzword IoT has kind of driven me crazy, I think, for the last 10, 15 years, however long it's been used. And I think Edge AI is kind of getting in that same kind of vein where it's being used on everything. How would you define exactly what Edge AI is?
So that's a great question, and I do think it's absolutely worth kind of clarifying that, or at least specifying that within the context of this conversation, because I think actually it means a lot of things to different people today. Basically, at the very, let's say, the most broad level, it's everything that's not in the server somewhere or in the cloud somewhere. So it could be your phone, it could even be your car to some people, where there's some kind of local processing happening. It could be in the back office of a retail establishment, for example. But when I talk about Edge AI and what we're doing at Infineon specifically around Edge AI, we really mean like in the end application, really close to something that is interacting with the person directly. And even though, and that could be a consumer device, it could be an industrial device, but those devices may, and frankly speaking, will often still be connected to the cloud, but they won't be relying on the cloud for their intelligence or for decision making. So that will all be done locally. And there's other benefits of being, still connected to the cloud. So that will often, in almost all cases, still happen. But the key thing is to bring value by making the decision locally. And there's lots of benefits of doing that. And I think we'll get into that maybe a little bit later, like what are the benefits of doing it locally on the device near the end application or in the end application. And I think today, at least in the context of the questions that we're going to be discussing, I'm going to be talking about that use case for Edge AI.
Yeah, I think that's what's really most interesting is, from the standpoint of really in the past, we've thought AI needs a very sophisticated processor in order to run a memory model on it. It's going to have a lot of memory and a lot of things. The model's going to be huge. The processing required to actually run the neural net on the model is going to be huge. Now we're seeing, I've seen 50-cent MCUs able to run very simple neural nets of different types. It's amazing what can be done. I think that's where Edge AI is changing a lot. And, I've had a lot of conversation with engineers that are building products at Future's customer base, talking with them about, hey, are you looking at Edge AI? And let me show you this from Edge AI and what Edge AI could do in this. And a lot of the response I've seen, even from very, very large companies that I think have great products and great strategies and forward-looking strategies, the answer from even the vice presidents of engineering and the CTOs is still, Todd, that's great. And you're like the fifth person to come in and talk to me this week about Edge AI. And we're looking at it. And as an engineer, I think it's really cool, but I don't really know how we're going to implement that in my product. And honestly, I'm getting to a point where I feel like maybe I'm being left behind because I can't quite figure out where edge AI fits into my next blender or washing machine or refrigerator or industrial control device of whatever it might be. How do you see embedded design changing products going forward? And where's some of the major markets and applications that you're already seeing successful adoption and you think other companies should maybe keep in mind?
So this is a great question, and I can tell you, I speak to some of those same developers on a regular basis as well. It sounds like, um, and I would say that there's, first of all, from an application perspective, but I do want to talk about the developer or the engineer here in a minute specifically as well, and what this might change for them. But from an application perspective, I think the way I look at it is that there are things that applications are quite capable of doing today. Um, from an end user perspective, but perhaps by applying ML or AI to that same functionality, it can be done better, or it can be done faster, or it can be done lower power, um, and it can be more future proof. And a very specific example of that, and it goes directly to your question around where do we see this adoption? I think one of the key areas of adoption right now is around audio. Okay, and perhaps there's some DSP engineers out there who been doing audio on DSPs for 15 or 20 years and
Mhm.
really believe like that's it. We've mastered audio using DSPs, and I would say yeah, we have. But you know what? There's an easier way to do it, and that easier way is here today, and it's going to keep getting easier. And that's using ML to do that, whether that be voice or speech recognition or audio processing or noise suppression or beamforming. So all of these things that, yeah, they exist today. You can do them today still without ML, but applying ML can make it again either be more efficient, so more power efficient in how it runs, or more accurate in terms of a result, or more flexible in terms of an implementation, and more future proof for how these systems will be designed in the future. So I guess trying to answer that question in terms of end application, audio happens to be one of the areas where we really see a lot of interest in this, and it's really a game changer capability. And that in that case, then again, it's not like, oh, I've created a new capability in my device, because there's lots of audio devices out there today that have some of these capabilities built in. But the next step then is, okay, well, now I'm using it. Where else can I use it? Or what features can I make better in my device or my end product for the consumer or in an industrial application? So there again, you can add more intelligent, make your devices or your end application more flexible. So for example, simply adding more language support or more accent support when it comes to audio, as an example. So a more flexible implementation can be brought with ML. Um, so that's kind of the next tier is, how do I make these things better with ML? And then it's really, what is it that I'm not doing today that I could do in my application if I used an ML data set, for example, to create a model around what I'm doing. And there, I think there's a lot of, if it's in the human world, I would say it's like this friction-free interaction. So the end device being more environmentally aware, meaning what's happening in the environment around it, and then being able to autonomously make decisions around what the user may want or prefer. And if it's in an industrial environment, it might mean removing physical controls or improving safety or removing inspections. We have a very interesting use case, for example, where we had a manufacturing line look at how to improve weld quality through the audio sound of welding happening on their manufacturing floor. So in those cases, it's like, well, we haven't been able to do that before, but now we can add this capability to these products to make them do things that they weren't able to do in a more traditional embedded approach. Now I wanted to go to the embedded engineer piece, because I believe this is something that it's coming so fast, especially in the last maybe 6 months, in terms of how code generation has accelerated. But it's not just code generation; it is the skill set of an embedded engineer that's changing drastically. And I like to give a real world example that that we use internally in terms of some of our products. So Infineon has a pretty broad portfolio, and I'm on the here's talking about the microcontroller and connectivity piece of that. But we also have sensors like radar, for example. And I would say if you go back in time 2 or 3 years, when we took a traditional kind of embedded approach to connecting radar to a microcontroller to do some kind of processing around, for example, activity detection or presence detection in a traditional embedded way, that took a lot of work and it took a lot of expertise on both ends of the equation. So there's a lot of expertise around radar and how those sensors work, and then all expertise on the MCU and how that embedded piece of it works. Going to a different programming model, meaning I don't say it, one based on a data set that creates a model that solves that problem that an embedded engineer was trying to do through, I'll say a more traditional coding approach, has really simplified the development. And as a specific example, we have these higher performance Edge ML MCUs called PSOC Edge, and there we hook up our radar device. An engineer can determine, okay, I want to use that not just for presence detection, did somebody walk in the room, but now I want to use it for gesture recognition as well. So turn the lights on, turn the lights off, or whatever that may be, a set of gestures, right? Now it's not a matter of programming it, it's a matter of creating a data set around what these signals look like to that sensor, creating a model, and then putting it onto the MCU to run. So the development environment changes because of that, but also I would argue the development approach is simplified because of that. And I can tell you from a real world perspective, some things that used to take us, and again, we're the product experts because we build those products, maybe would take us months to develop, is now literally taking us days. So I think that's a big deal for developers. The other thing that I want to mention that I think, and you mentioned IoT, and I've lived that journey as well. But there is something, obviously, technically it's a very different field that we're talking about. But the other thing I want to mention in this context around the developers and what the opportunity is for developers in this space is that we are really experiencing what I would call like the perfect storm right now. And on IoT, I can tell you, years ago, it used to be a little 8-bit MCU, maybe with 32K of flash and a radio attached to it that would open your blinds and close your blinds, right? Now it's a 32-bit MCU, maybe multi-core with 1 or more megabytes of flash on it that, to support Matter to open and close your blinds, right? So what in a traditional application space, and it's the same with PCs and it's the same with phones, the processing performance keeps going up, the memory requirements keep going up, but the end user experience, one could argue it's not really changing that drastically. For Edge AI right now, the opposite is happening. Yep, the products are getting better and higher performance and more capable, but not necessarily through a brute force approach, need more megahertz, but through an intelligent approach around NPUs for these neural net processing. But the other thing that's happening is that these models are getting smaller and smaller and smaller that are running on these devices, and the tools that create those models enable developers are getting better and better and better and easier to use. And I think that's really a revolution that's going to spur a lot of opportunity for developers to create really innovative products going forward. I want to tie that back to a comment you made earlier about large language models. It hasn't been that long since that technology or that capability existed. And a lot of people still do think about, well, that's only in the cloud because of this huge processing performance. But we're actually running what we call edge language models on MCUs now at Infineon. Now, we're not going to ask an MCU to give us a thesis on the U.S. Constitution, for example. But if I know that MCU is going to go into a thermostat, I can ask it pretty much anything I want about that thermostat, whether it be related to the user manual or the usability or what's happening in the weather, or give me an efficiency suggestion, things like that are relevant to that application. And that can run all locally on the device now. So pretty big changes coming pretty fast.
Yeah. I mean, the amount of features that this is going to allow in so many devices, it's mind-boggling. And I think we're really only limited by our creativity, which is part of what's exciting and partly also can be a little bit scary, because we've got to be thinking creatively as engineers to outpace our competition and make sure we've got the right product out in the market. And I think we talked a little bit already about, that move from, traditional microcontroller design where you've got deterministic deterministic code, and you know exactly what that code's going to do. If the temperature hits this point and the humidity hits this point, then my device is going to do this every single time. I know exactly what that world looks like. Now that we're getting to a point where you kind of are using some kind of a model to do that for you, there's a little more gray area. You don't know exactly what the device is going to do in every single situation, and you're kind of losing a little bit of the control, I think, of your design, if you want to put it that way. Exactly how it's going to behave, and kind of trusting in a model to take care of some of that stuff for you. What are some of the architectural and design surprises that you see engineers run into a lot when they're designing their first AI or machine learning based design on an MCU? And how's Infineon kind of helping with those?
Okay, that is a great question, and frankly speaking, it's one that's on my mind pretty regularly. As you know, here in Austin, we have a lot of these self-driving taxis, right? And the Infineon office happens to be seems like it's like the center epicenter of the training ground or whatever. Like there's not a commute to work where I don't see like 5 or 6 of those on the road. And I think I spent some time in automotive MCUs 15 years ago or so, and there was a time where like every line of code had to be known, and as you said, had to be deterministic. Like it was known exactly what was going to happen when it went into a car. And now we have cars driving themselves on the road, and you don't know I don't want to put fear, uncertainty, and doubt about the technology out there, but it's not the same, right? Like a mind shift has taken place in the industry, and there are some controls over that around how we as developers build in still a level of safety or repeatability or determinism into these systems. Now, what I do see, to answer your question specifically, is where that one of the biggest aha moments or challenges that developers have is like, oh, I got the model running on the PC, or I got it running on my desk on the EDK, for example. And now they go and they put it in the form factor, they put it out in the real world. And as an example, let's just say we wanted to do a camera-based doorbell that was going to recognize, or a smart lock that was going to recognize it's Todd that's walking up to the door. Go ahead and unlock it when he automatically, right? And we do it on the PC. Everything is great. We put it on EDK in the office or in the lab. Everything is great. We build the form factor. Maybe it gets a little bit wonky, but we can tune it. Still working good. And then we put it outside for the first time. And for the first half of the day, it works great. And then all of a sudden, the sun starts to set, and it's behind the user, and all of a sudden, it's a shadow. And so this is where we see that step going from kind of the lab or the proof of concept, which I think most developers can get to, frankly, at this time with the tools available, tools and software and open source models, for example, can get to that proof of concept pretty quickly. And then it's like, now I got to get it across the finish line where it's going to go into a real world environment, and I can't control everything like I can in the lab. And that piece is where it takes some time. And what we see then is, developers needing to find ways to simulate what is going to happen in the real world so that they can enable a broad range of testing environments for the end product, so they can have confidence in how it's going to behave. And then, of course, I don't want to say the bigger the data set, the better, but the broader the data set in terms of innate or covering those different corner cases of how it might be used in the real world also improves the robustness of the solution.
Right. And I think the model question is the other big one. Is it what I've seen a lot of the customers that we've been helping get through their first edge AI design, they've been using publicly available models. And a lot of times there's enough models out there where you can do a lot without having to create your own data set, like you mentioned, large data sets and do that. But occasionally some customization needs to be done. And occasionally a publicly available model doesn't exist at all. And you do need to take a large data set and create a model from the ground up. How's Infineon helping with that, whether it be customization of an existing model or actually, taking, a bunch of data and creating a brand new model for a customer engineer?
Yeah. So at a very high level, we have a solution called DeepCraft AI Suite. And in that suite, there's different pieces to solve different, I'll say, problems that you just brought up. But at the first level, in that suite, there's something called DeepCraft Studio. And DeepCraft Studio is really a start wherever you are in this development and out comes a model. Okay, so if you're at the point where you have a data set, or frankly, even if you're behind before that point, which is now to need to create some data, it will help you do that as well. But let's just say you have a data set, you bring that data set into this tool, it will help you label and then auto label the data. So what is it you're looking for in that data, and then it will you can use that tool then to create the model and to optimize the model, for example, then get it onto the target MCU. So there's that approach, and then there's this other approach where a customer already has their own model, for example. So within that suite of tools, there's a model converter that will take an existing model that a customer may have in called a standard format and convert that to run on one of our MCUs. And then the last piece that I'll say is, they have like you said, and maybe something out of open source, and take a very similar approach. Like I have something that exists, and now I want to test that or benchmark it or see how it runs on your product. So we offer a tool within the suite to do that as well. And then what I would say, and then absolutely there's a lot of open source stuff, but we also already offer a lot of, I'll say, proven models that running across a wide range of applications or use cases on our devices. So we have we call it the AI Hub, which is basically a large model zoo of already kind of Infineon curated models as well that customers can play with or use, frankly, in the end.
Okay, that's incredibly handled, and I think that's for me the biggest thing. From my background in embedded engineering that I look at as I'm moving into this, if I were to start a new project today, I think the biggest thing that is going to influence my MCU selection and what I'm actually used for the brains of this new product is that ecosystem. And to see Infineon investing in that, I think is really exciting. That's going to be the biggest thing because you're going to spend 80% of your design time in that firmware, messing with the model, trying to see if the model really works in all the potential, ways. And so the hardware becomes much less important than that ecosystem that exists. So really exciting to see you guys do that. And I think it's going to be important that engineers know, okay, if I've got this large data set, what do I do with it to create a model? The fact that Infineon has that capability, I think, is absolutely huge. So, as we're doing edge AI designs, is there a balance that needs to occur maybe that's different from our old deterministic type designs? Now, we've got something that's running AI, it's running, we've got a little bit less control, as we've talked about, over exactly what the firmware is going to do because we do have some kind of an AI model that's making decisions that we don't always know exactly what's going on there. Also, to your point, most of these devices probably are still connected in some way to the cloud via IoT. So yeah, the models resides locally on our embedded system, but we're still talking somewhere out there. And so is there more, of a concern about security issues, and maybe more severe issues that can run into with our designs because of, again, this ability to be a little bit more autonomous and also the fact that it's still connected to the rest of the world and potentially connected to bad actors?
Another great question. So the answer is yes, and there's another, let's say, new, I'll call it a pressure point on security on these devices. So first of all, I would say that the basis is for any IoT device, right? There's a certain level of security requirements that are just, I would say, inherent to that design in terms of protecting the firmware and protecting the device. I will say to build on that, then, so first of all, when you're doing these things at the edge, and if I go back to that door lock example, right? There's a privacy aspect of it, which is I no longer need to send what my camera is recording to or my camera is seeing. I don't no longer need to send that to the cloud to get processed and then potentially lose control of that between the device and the cloud or even in the cloud. So that the data can stay local in this case. So there's a inherent, I would say, privacy advantage already because of the edge aspect of this. Now, the other thing that I wanted to layer on top of this in terms of the security above and beyond the traditional IoT security for an end device is that traditionally, a customer may have an MCU, let's just say 256K of code that they developed, and maybe it took their team 6 months, let's say, to develop and tune and qualify that code to run in that application. And not to say there's not value in that, But compare that now to a developer who spent maybe 3 years and millions of dollars to collect a data set for their application, and then they create a model. The value of that model can be pretty high, frankly speaking. And how do they protect that model or be sure once they put it on that device that it is going to be protected? So what we're seeing is an up level in terms of the fundamental security requirements, but is also the I'll call it the things that need to be protected. So, for example, if I talked about that 256K example, well, that's all locked down on the MCU, right? I don't really need to worry about is my external memory secure? Is it encrypted? And when it gets decrypted on the device, what does that mean for performance? I didn't need to worry about that in the 256K world. I absolutely do need to worry about it now if I'm talking about megabytes of an ML model sitting in external memory. So what we're doing and what we see this trend coming is, we worked with the industry we were one of the lead players to create the level 4 PSA spec. Our devices are PSA level 4 with the vision or the view that, boy, what's going on these devices, but from a developer perspective, is going to be more and more valuable. But how to protect these devices in the real world is also going to be more and more challenging. So we needed to up level the security capabilities of those devices. And I will say, not to put a buzzword out there, but that includes now PQC capabilities as well, because that's coming, right? And these devices, especially in the industrial space, may be in the field for 10 or 20 years. And at that point, we need to make sure that those devices are still secured.
Right. Yeah, absolutely huge. So let's go back to the hardware maybe as one final question on this, and let's talk a little bit about, obviously Infineon's MCU in this space is the PSOC Edge, and something that I think was a leader in the hardware space, coming out with some great capabilities there. And now we've talked a lot about the ecosystem that wraps around PSOC Edge. What do you think is really the benefit? Why should an engineer be considering PSOC Edge over some of the other hardware solutions that are out in the market today?
Yeah, so I think it depends on how you would compare it. But one thing is when we set out to define the family, we really I don't want to say made a bet, but we really said, what the future is going to be neural net on the device. So these devices are optimized for that, both from a hardware acceleration perspective, but also how we define the architecture and also how we define the security around this, right? So really making it a complete solution and thinking it through from that regard. The other thing that we're really seeing, or place where we're really seeing these devices today shine in the market, is what we would say ML efficiency. So really being able to get an ML workload done in a really low power budget. So there we're seeing things where we're enabling use cases that really don't exist today in the market. So for example, always on voice. So there's a few devices like your phone that that's an always on, or if you have a smartwatch, maybe is an always on voice product. But in the end, that thing is getting charged every 12 to 16 hours. So every night, my phone goes in the cradle, it's going to get charged. But we're talking about being able to enable devices to last for weeks without charging, but always be listening. And it could be for voice, it could be for any other kind of audio event as well. So this low power audio processing specifically, but in general, super power efficient ML is a place where we're really seeing the PSOC Edge family resonate with developers.
Yeah, agreed. And I think that, again, like I said, I think the hardware is great. You've got a great ecosystem, some great development platforms as well. So really is a powerful place, I think, for engineers to look if you are going to be starting a new embedded design and you're looking at doing AI or ML for the first time. Beyond that, I would say, look, I hope everyone kind of enjoys as much as I do hearing from Steve, true expertise in this area amongst Steve and amongst so many other engineers at Infineon. So Steve, thanks so much. I feel like I could talk to you about this for another couple of hours. This is just such a fascinating area, and I want to keep picking your brain, but I really appreciate your time with us on The Current today. And thanks so much to our audience for joining us on this. I think, again, there's so many things to talk about when we're looking at Edge AI. We're looking about bringing artificial intelligence into our embedded designs. We here at Future Electronics are here to help you with that. We have a tremendous amount of engineers on staff who are spending a lot of time learning about this this technology and are ready to help you get set up and moving forward in your project. So if you have any questions, if you'd like to speak to another engineer to work on something, to bring some ideas forward, or just to brainstorm a little bit, we'd be happy to speak to you. Please reach out to us at Shaping the Future, one word, Shaping the Future at futureelectronics.com. And we'd be happy to speak to you about the designs that you have coming up. Thank you so much for joining us on this episode of The Current, and we look forward to seeing you next time.
Thank you, Todd.